what is gravity, and thereby the gravity constant physical meaning. Now, all of chemistry and physics is based upon some basic concepts. And we don't have to go too deep into this, but you do have to understand multiple things. First is the atomic model. And that's the 3D engineering, how we build a nucleus with electron shells and so on, and then how those are going to interact with here, a remote set of the same sort of things. That means understanding the fundamental forces. So you have the electrostatic and the nucleostatic. And that's the strong nuclear force and the weak nuclear force. And then finally, in the little part just at the end to get the numbers match, you have to understand that the electron subshells are two cylinders, and that is two hemispheres, where you have the Pauli pairs at 180 degrees, which makes the electrons as far from each other as possible, but still net two force attracted to the nucleus. All right, so what is electrostatic versus gravity? Well, it's a reduction of that electrostatic force, okay? The radial electrostatic is basically a 1/distance squared formula based upon the Coulomb constant. But the Coulomb constant is really Planck's constant, which is the energy at the equilibrium distance. Now remember, in my teachings, Planck is always at the Bohr radius for hydrogen. And that's the 1 proton, 1 electron equilibrium, the simplest system that we can do. And so that strength for both the electrostatic and for the nucleostatic, the strong nuclear force, that extra 1/r, are both the same, but in opposite directions, so that the electrons want to stay in shells. Okay? Now, gravity is also a 1/distance squared strength profile. Okay? But guess what? It's always 10 to the 34th power less than this. And so we need to convert why that happens. What is that 10 to the 34th? So I did this at 1 meter just to show the strength of the hydrogen atom in this calculation. The electrical charge, obviously, if it wasn't an electron and a proton, separated, okay? And the gravity force, which is the system of the pair of them. So strangely enough, and this is the introduction, it's not exact yet, that 10 to the 34th, if you think about 4/3 pi times radius squared, that is a volume. And that 5.29 is the Bohr radius that we just did over here, which is where the electron is versus the proton. So my preliminary things is that 10 to the 11th times to the 3rd power is 33, and then some of this is going to come up to about a 34, okay? And that's where we're going to end up, but there's a lot more to it, okay? But in general, the gravity force is the electrostatic force netting the proton versus the electron by the difference of the volume of that electron field that is pushed out by the second extra 1/r force. So let's look at this in a little more things. The traditional formulas are force equals KQQ, and that Q's are charge, and gravity is G times M times M, and the M's are mass. Again, both are over 1/distance squared, which is the profile of how fast they get weaker based upon the distance of the sets that you're analyzing. So that relationship, since that's the same, that relation is set as fixed between these two. And really, what's the difference between a charged particle and a mass particle? Well, this one includes neutrons, and that one is just electrons and protons, and this is electrons, protons, and neutrons. Now, In my field acceleration physics stack, you can get this by using hc, that's the Planck's constant, times the speed of light. And you'll find both hc, h hat c, h, and h hat at various points. And it depends on which formula you're looking at which level of the stack, at a field or acceleration, which one you use. But you'll see these 4 Planck constants continuously used in physics. And the position in the field, that equilibrium, that's the Bohr radius called A sub O of hydrogen, versus the edge of the particle, the radius of an electron. Because if you move that field at 1 over distance squared up from at that distance all the way till where it's the edge, that's the maximum strength. And that is it. And of course, as I said, for the 2 cylinders, you're going to have to do this adjustment factor of 8/7 later on. And this is the anomalous moment, which is very advanced stuff. So what is gravity? Let me go again. You see, if we start at 0, the electron, the proton, has a certain field strength, okay? But the electron, it's in a shell, so it really doesn't start until here. And so its electrostatic force is like that. And if you net the 2, that is gravity, the green line here. And that difference is pretty material. Now, you can't calculate it inside because obviously the electrons are on different sides. So let's look at this a little bit differently. If you have at time 1 or time 2 or rotation 1 and lots of different atoms at different orientations, you have the nucleus to the other object, but this one's a little closer and this one's a little further away. But overall, the average of those, because it's 1 over distance cubed, becomes this. So what I told you in the first slide is going to get adjusted a little bit. But basically, that distance is going to be that 4/3 pi times the Bohr radius, adjusted because there's a pair at each side, a poly pair, which pushes this volume out a little bit extra. Now, what is that Planck-At-Edge, the radial electrostatic? This is a concept called charge, but again, this is the Planck-At-Equilibrium, that's h hat c, at. And I'm always going to call it Planck-At-Equilibrium so that we remember that it's relative to a position in the field or acceleration, again, depending on which formula or equation you're using. So Planck is at the equilibrium, the Bohr hydrogen radius. But charge is all the way up at the edge. And it doesn't matter whether you're an electron or a proton, that distance is the same. It's r sub e. And thereby, this relationship does. And that is that, and strangely enough, if you have this relationship, it's r sub e over a sub o. And it's the square root because the formula is 1 over distance squared. Now, for a long time, they've called this ratio alpha. And this alpha is called the fine structure constant. Now, I hate that name. As you can see, I cross out constant because this is the equilibrium versus edge fundamental scaling factor applicable everywhere. So you're going to find these alphas, but remember that I'm always going to present them as a scaling ratio. That scaling ratio is very critical to get us what we need, okay? And so you're going to find that application all over the place. And remember that oftentimes it's square rooted, so you'll get a over 2, but that's really just because they're analyzing it within that scale. So what do we do? Understand that I only want Planck, and I only want that scaling ratio. All these other constants go away. So this K, which is the Coulomb constant, and even this charge, I'm going to replace. Okay? Now you can do it this way. They also have this other one which would be called the permittivity of states, another mixed constant that in every case in the field acceleration physics stack you eliminate, because that way you get down to the fundamental concepts and the physical model. So by this step, I basically can substitute in the wings that we know, and in the end, you end up with that H hat C, and you don't have charge anymore. You have the number of particles of charge on each of the items, and then you have that square root of A sub over R sub E. And again, remember, they're going to see it in the textbook probably as 1 over alpha, the fine structure constant, times 1 over R. And this is the potential level. And understand in the stack there's potential, force, and field. And in my stack, there is position, velocity, acceleration, and field. And there is no force, and there is no mass. The object of my work is to eliminate those concepts of charge and mass and get down to number of particles, and working only in Planck's constant, one of the versions. So that was nice, but in reality, again, I like scaling constants. And really that means that this R is relative to the upscaling from here to there. And then you have this 1/2 factor after. So I split that square root into 2 items. And this has to do with moving between the layers, because at the potential layer, I'm not necessarily at the correct layer, and we're going to have some calculations for that. Again, H hat C is a strength constant. That is that. That's always measured Planck at equilibrium, Planck at Bohr. Okay? Then you have the count of particles. Everything becomes quantitized because you only have so many electrons or so many protons, and it can only jump in these integer units. Okay? So there's no 1.27 particles. It can only be integers here when we use the m. Okay? And then you have the radius, but you have to use the radius basis the scaling constant as to get from here to here. It only works if the slope of, not really, the shape of that field is appropriate. Okay, so let's talk a little bit about these different scaling factors. And I talked about how we have. Basically, we have in the current model, they use potential, force, and field. And remember that I use only acceleration and field, eliminating this and that, and obviously field, acceleration, then velocity and position become the traditional math stack. And this simplifies a lot of projects because that variable mass goes away. All right. So obviously we know that in the potential, it's the electrostatic is 1 over R. In force, it's 1 over R squared. And obviously the field is 1 over R cubed. I'm just doing the distance formulas and not worrying about the constants or other factors like when you do the integral, you get a -2 or something like that. All right. The nucleostatic, which is strong and weak nuclear force, is also called an extra 1 over R and called Bohr angular momentum, or is, and basically it's the offset to that. In the radial direction, that's why there's an R here, radial electrostatic, radial nucleostatic. These two are opposite, and that's strong in that, and that's what causes our electrons to stay in shells. 2 opposite forces come to some equilibrium distance. All right. Now, nucleostatic has this formula from Yukawa potential, and but they actually changed this mu, which is the mass of the elementary particle, and the values of that in electron volts is 134.7 with the naught, or the 135, which averages, guess what, to 1 over alpha. And so thereby you end up with e to the -r over r. And one of the magics of this formula that they love in statistical mechanics is that when you take that integral of this exponent to the EX so that you can do statistical work, it becomes 1 over B times the same formula, okay? And so effectively you can get to a 1 over R. This becomes 1 over R cubed, and that becomes 1 over R to the 4th. And all of that is what Bohr was saying is there seems to be an extra 1 over R. And now he wrongly attributed it to a gravitational orbit, and we get those wrong names called orbitals. I don't call them orbitals. Only use the word subshell because it's not a gravitational orbit, okay? Now, the thing is, as you're analyzing this, you have to do the net of these two because you're trying to find positions as these interface. So what happens is you end up with the 3 over 2. So you'll find that the scaling factor, instead of being just the distance over the distance, or the square root of it, you'll get 3 over 2 for that. Now, you'll also see this often as the 1 over alpha. Again, I like this because then you know where you are in the field and you can evaluate the particular event you're trying to understand to see if one of those two needs to get substituted. Often the A sub O is not the place where the transaction is occurring. It's occurring out at the outer shell, which is further out, and thereby you have to apply the correct position within a field. All right? Now the thing is, if you're in the field level, you'll end up with A sub O over R sub E, but the transition is 4/3, okay? And if you're trying to do mass, you're going to end up with A sub O over R sub E to the 3/4 because you're going the other direction, okay? Which instead of flipping the exponent here, I flip the 1 over R with the same effect, okay? Again, I use this, but your textbook will probably use this formula. I believe this tells you the physical model of position within field that will help you everywhere. This ratio, A sub O, Bohr radius of hydrogen, the equilibrium, over the edge, radius of electron, to the n power, depending on what you're trying to do, is the scaling factor. It is universal in all of physics. You will find these alphas, and which I always substitute, of course, for this, because it helps explain a million things that are going on, because you can see how the field of string is going to change how the particles interact, their behavior. All right, so now finally, after all of this, I can get to the gravity constant. Okay, gravity constant. Now again, I started this. Remember how back here, I got this into units of charge particles, Q, but no longer charge. Charge is gone. The same thing happens in gravity. This is a number of mass units, okay? So we start out with the electrostatic force. Remember that H or H hat C, okay? Now in this case, I've taken that H hat and I've split a 2 over here and a 1/2 for the integral. 1/2 integral of 1 over x squared will integrate nicely up to the field level, okay? Okay, and you've got that scaling factor. You can see that all over the place. But you also have an adjustment here, which is called the anomalous moment. And that's, once you have those things at that difference, but those particles themselves actually have a radius. And so you sort of like, you've got one pole at one side and the duopole, the Dirac monopole, which I think is a duopole, at the other. So you got that, I think I did that back here. Here, think of this as a monopole. So instead of doing this calculation, you have to do an extra calculation at R sub, this is the radius of that sphere of electrons. But here, I have to do another calculation of there versus the other side. And so Schwinger, Feynman, and Tominaga did some great work, got them the Nobel Prize basically to explain that ratio, and it's called the anomalous moment. And so it's a tiny adjustment. You can see the number here, 0.0011589, okay? Now, there are a couple other parts. Extra 1 over r field. And this is how I get rid of the mass particles, because the mass particles are the push out of those extra nucleostatic acceleration. So that field is at a fourth there. And again, so there's that a sub o over r sub e scaling factor, but I have to do this tiny adjustment. It's at the 3/4. Guess what? That's because I'm at the acceleration level. Now, that is the field. This is the 1 over m function that we hear of all the time, okay? Newton's second law is really the start of the problem, because he didn't know about these tiny particles within there, and he did great for his time, amazing. But his mass goes away when you have this understanding of this balance of those two forces. So you have to have what pushes out those things, and that's units of the field at that scaling factor. Now, once you push it out, you then have the volume of that subshell, which is no longer in the field. So this original electrostatic force is reduced by the volume, 4/3 pi times radius cubed, okay? There it is, okay? And again, this is the scaling constant, because the radius obviously continues to change all the time and such, okay? And so then you get, this is the rest of that electrostatic scaling factor applied to the distance, squared, as we talked about, and those sorts of things. But this volume, 4/3 pi r cubed, is how we do it. Now, without the anomalous moment, that number comes out to there. In fact, I can actually show that to you, I think here. Here's Wikipedia, which has a theory of everything. But you see that little citation needed? That's me. And it isn't in Wikipedia because they came up with this number 21 over 2 over 1 over alpha squared. Now remember that alpha is already a half, so it's there. So 4 plus 3 is 7, and 7 to the 3/2 is 21 over 2. So without the anomalous moment, which is what Wikipedia has as that result, 6.792, okay, comes to this number, okay? Now, when you correctly say that you're going to get the extra interaction for the particle radius scaled that far away, you actually take that number, but that is again at 3 over 2, so this 21 over 2 becomes 63 over 4, okay? And so you take the anomalous moment, this tiny adjustment for the radius, which is based upon Schwinger, which again is this ratio over times 2 pi, which is that particle as that field, that nucleostatic, the axial nucleostatic field rotates around. It adds this little harmonic, which Schwinger called, Schrodinger called a Beelzebub, Zitterbug, and which they called the anomalous moment. And they calculated properly, but using the abstract constant alpha instead of the actual physical model as I explained it. So as a result, you then take that number, reduce the number that they've got by that factor, and then remember that that distant particle also, because you're left with the distant particle, also has that Schwinger calculation. And you end up with 6.6422. And guess what? The coda value is 6.6730 with a variance of 15 out of that 30. So that means I have a result that's within 0.7 parts per million to the observation, and the precision range of that observation is 22 parts per million. So I'm within 3% of the exact center of the current range that they're not even sure of, okay, within that. So within that 22, I'm within plus or minus, I'm within a tiny difference of that. This number has done it. Most importantly, it has given you a physical model based upon understanding 1 over the nucleostatic field as the function of what is mass, which I'll have to cover in another video, and the volume which that shell then pushes out, so that you end up calculating the gravity force and gravity constant based upon the electrostatic constant. Okay? Now, earlier I talked about that we're going to eliminate these things and understand. So that 1 over r, which Bohr called angular momentum, and it explained everything like that. Plus, acceleration equals force over mass is Newton's second law. And amazingly enough, out of all of Newton's great stuff, that's the one I have to fix. So, but remember that force equals GMM, and we keep using this, but I prefer all work to be at the acceleration level. So you use the force divided by the mass squared. That's that extra 1 over r field at the 1 over distance squared. And that becomes, guess what? M1s cancel. So the only thing that's important is how many particles are in the other project pulling you along and how far that distance is, because that's the electrostatic field. And the G is doing the netting for your big nucleus proton charge versus the electron, and scaling it down by that 10 to the minus 34 factor. Now, the last thing, just to go a little further, is that this also explains why mass is different. You see, the proton is the center, and with the big counts, that becomes the dominant field in this system. So that scaling factor of A sub O over R sub E to the 4th power is the overall scaling factor, okay? And again, we're going to go back to those different relationships of squares, cubes, and things like that. Now, if you take charge, this is the charge one that I did. If you take the charge at equilibrium, the Bohr radius, that's that. The particle edge, okay, that's there. Then you get this ratio. And guess what? That happens to be A sub O squared, or alpha squared squared, which is 1878 squared, which is that number. And that's the difference in those charges. So charge is really the radius, but using the scale of those two distances. The fine structure constant is the Equilibrium-Vs-Edge Scaling Factor. It's the ratio of two distances, and thereby very able to be understood as a physical model in the position in a field acceleration physics stack. So what happens with mass? This is charge. Mass is a little more different because we get a different one for the proton versus the electron. Okay, we already did this 1878. That's the squared versus the cubed, okay? And obviously the extra amount of that factor to the 3/4, the extra R1 over R versus the R is 1/4. We see this number all the time. That is the fine structure constant, 137.05. Now, obviously, if you're working in the cubed layer, it's already in the electrostatic, so we don't do that. But now when we have that field at the fourth layer, this is the extra 1 over r, at the field lever, you're basically taking this 1878, squaring it, cubing it, quadding it, okay? But then you have to really take it to the 1/4 because you're just doing the extra amount. 18,778 to the 3/4 is 16,014, okay? And that's the ratio of the mass of an electron for hydrogen. But guess what? Not everything is at hydrogen. In fact, most things are in poly pairs. So first we have to understand that the electrostatic repulsion pushes electrons as far away as each other. It is electrostatic attracted up to that extra 1 over r wall of repulsion at the Bohr radius. And so as a result, that's again a squared versus a cubed. And the cubed is the repulsion that's missing because an electron to electron is the same field and does not express nucleostatic. To express nucleostatic, one of the particles has to be a color particle. And I think your textbook actually says it's an interaction of color particles, but I disagree with that. I believe only one of the particles has to be a color. So a proton or a neutron with an electron will express that extra 1 over r nucleostatic force as the opposite, thereby creating this huge 1 over distance cubed as you get closer actually becomes bigger. So then you get 1 over distance 1 versus twice, because that's all the way on the other side. They want to be the same distance, is 1 over an eighth equals 7/8, or 8/7 the distance. So as a result, the volume of that cube is not the Bohr radius, but the Bohr radius times 8 over 7. So, and that's based upon a physical model of poly-hemisphere pairs at 180 degrees. That there is a physical model that all the periodic table is based upon hemispheres. 2 times the squares. 2 times 1 is 2 electrons in shell 1. Then 2 times 2 squared is 2 times 4, 8. 2 times 9, 3 squared, equals 18, 32. All of those shells are based upon 2 hemispheres times the squares. One dimension is 2 hemispheres, and the other dimension is the tightest configuration. Pi r squared, because it's a circle, is the most compact filling. Okay, so now what happens, instead of that 1664, I multiply it by 8/7, and I get 1863. And again, I've got to have that Anna-Miles moment because those particles themselves actually have physical distances. So I end up with 1836.16, okay? And the experimental value of the ratio of the proton mass versus the electron mass is 18,365.15. And I still haven't figured out why I'm off, but that's down at 5 digits, okay? So this is the limit of how far I've gotten in my work to understand gravity and ultimately to eliminate all mixed constants and to work only with Planck at Bohr, Planck-At-Equilibrium, and the proper scaling reference, which is Bohr versus the particle edge, appropriately scaled within a field acceleration physics stack. So one of the great things here is that effectively I've proven something that's been a big thing. Gravity is based upon electrostatic force. It is not a separate force. Your textbook that says there are 4 fundamental forces is wrong. Gravity is electrostatic force. It's just the net of the proton versus the electron as we organize the atomic model, okay? Further, gravity is a mixed net-to acceleration. Obviously, that makes it possible of being variable. Mass is also. Charge is that Planck at Bohr upscaled, okay? And mass is Planck and Bohr upscaled, but for the extra level. So it's just 3/4 because you already did for the charge, which is usually where you're starting. So this just gets you from the up to the cube for electrostatic, and then you go from cube to fourth power. So it's there, okay? And that 3/4 becomes the scaling factor of the position within the field to explain the difference in mass, and thereby done that. And finally, my gravity calculates as the net 2 force, and it's within 7 parts per million of all the observations. Thank you.